Okay, so we're still on proof by divisibility. This is our second example, and in this example it's slightly different to the last. So the last example, what we had was, so in our last example, or example 1, we had 4 to the power of n minus 1 divisible by 3. So that was our last example. Whereas this time we've got proved by induction that 10 to the power of n minus 7 to the power of n is divisible by 3 for all n element of n. Okay? So the first thing to note is that n is, again, is the powers. We got the word divisible this time, so divisible is telling us what type it is, and then by 3. So this is 3 is come up again. It's not going to be divisible by 3 for every single question. It just happens that the first example and the second example we've done is divisible by 3. But divisible here is your buzzword for it being the type 2 proof by induction. Okay, and the fact that we've got powers as well. Okay, so we'll start off with our to prove. So we'll get our, so to prove is that proposition n 10 to the power of n minus 7 is divisible by 3 for all n element of n. So we're just repeating our question, and then we're going on to 1. So first one, show that proposition of 1 is true. Move it that way. So show that the proposition of 1 is true, and we're going to fill in n as 1. So proposition of 1, 10 to the power of 1 minus 7 to the power of 1. So proposition of 1 is 10 minus 7, and proposition of 1 is 3, and we'll check if that's divisible by 3, and it is. So 3 is divisible by 3, so therefore proposition of 1 is true. So that's our first part done. Okay, so show that proposition 1 is true. We go to our second part then, or assume that proposition k is true for n equals to k. And for everywhere we see n, we're going to fill in k. Proposition k, 10 to the power of k minus 7 to the power of k, is assumed to be divisible by 3. And then we're introducing our new thing with the a, and what we're saying is that 10 to the power of k minus 7 to the power of k is equal to 3, because that's what we want it to be divisible by. A, again, a is an element of z. So we want it to be divisible by 3, which is the same as saying that that 3 is a factor. Okay, so last time we had is a factor, this time we've got divisible, same thing, just written differently. So we're saying that whatever number 3 times a is, could be 9, it could be 12, we could have 27, it could be 30, 300. So this is a multiple of 3, so it's divisible by 3 if it's a multiple of the number. Okay, and then what we're going to do is we're going to isolate the bigger power, or the bigger number, base number. So isolate the bigger base number. So write that out. Isolate the bigger base number on the left hand side. Okay, so 10 is the bigger base number, so 10 to the power of k equals 3a plus 7 to the power of k. So we're just isolating that, we're manipulating this around, so or 2 hours, which means it implies, so therefore they're the same thing. And we're going to step 3 then. So step 3 is proving that proposition of k plus 1 is true for n equal to k plus 1, given that it is true for n is equal to k. And we're going to sub in k plus 1 into wherever k is. P proposition of k plus 1 is equal to 10 to the power of k plus 1 minus 7 to the power of k plus 1. And like before, we'll use our index rule and we're going to split up our powers using our index rule. So I'm just going to move this up a bit. We have it. And we're going to split that up. So proposition of k plus 1 equals 10 to the power of k multiplied by 10 to the power of 1 minus 7 to the power of k multiplied by 7 to the power of 1. So we've split up our in our powers into indices, and what we can do then is see from part 2 what we're going to replace. So we'll just move it that way. So what we're replacing is the 10 to the power of k piece here. So replace with right hand side of step 2. So we've got p bracket k plus 1 equals, so we're subbing in 3a plus 7 to the power of k times 10 minus 7 to the power of k times 7. So we're replacing that green box there, and we're going to multiply this piece out. So proposition of k plus 1 equals 10 by 3a, 30a, and 10 by 7k, so we'll just leave it as 10 times 7k for the minute, minus 7 to the power of k times 7. Okay, and we'll tidy that up a little bit more. So 30a plus, if we factorise out the 7k from both parts, so plus 7 to the power of k, bracket 10 minus 7. And then we can tidy this bit up. 30a plus 7 to the power of k times 3, because 10 minus 7 gives us 3. And then, like before, we're going to factorise out 3 completely. So 3 bracket 3 into 30a gives us 10a, and 3 into 7k times 3 gives us 7 to the power of k. And like before, this bracket, if we were given the two values for a and k, we'd have a different number. So we know this is equal to 3 times b, where b is an element of z. So again, if you don't get that part, that's okay. That's just us finishing off the end of the question. And what we want to do then is write the conclusion for the step 3. So we're saying, therefore, p, or the proposition of k plus 1 is divisible by 3, because we factorised 3 out in this part here. And then we're saying the proposition is true for n is k plus 1, given it is true for n is equal to k. And then we're going to go and we're going to write our conclusion for that question. So that was the conclusion here. That was the conclusion for part 3. And then we're going to go for the final conclusion for the total, or for the whole question. So 4 is our conclusion. And what you're basically doing is writing the conclusions for each step. So the first conclusion was that proposition 1 is true. And then our second conclusion is putting step 2 and step 3 together. So if proposition of k is true, then proposition of k plus 1 is true. So if we're assuming this is true, then this has to be true as well. And therefore, by induction, proposition of n is true for all n